Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
The cosmos is full of secrets extending from the backyard of our own solar system to the far-off beaches of the cosmic ocean. That's how it's always been, a spooky place full of mysteries and mysterious occurrences that will give you chills. Now, on board Voyager 1, one of the most famous NASA spacecraft of the 20th century, strange things are happening in the vast emptiness of space billions of miles from Earth. After 50 years of continuous flight, the most distant spacecraft ever built by humanity is still in operation. What's even more odd is that there are no indications of a malfunction or anything. NASA scientists are frantically attempting to determine the cause of this odd signal. What precisely has occurred then? What did this terrifying signal entail for the rest of us here on Earth? Come with us as we delve deeply into Voyager's historic journey to date, as well as the recent horrifying signal in deep space that has baffled scientists and experts. Voyager 1, which was launched on September 5, 1977, was designed to map the outer solar system, focusing on the gas giant planets Jupiter and Saturn, as well as Titan, Saturn's moon. Launched in the same year as its twin Voyager 2, it had a somewhat different mission: to study the outer planets before reaching the end of the solar system. NASA was at its peak in those years, having won the U.S. space race and successfully landed men on the moon a few years prior. The engineers at NASA were the world's envy. Both Voyagers had to travel through the asteroid belt, made up of rocks and debris circling the Sun, in order to reach Jupiter and Saturn. They had to withstand radiation from Jupiter, cosmic rays, and other space dangers. However, the two spacecraft arrived without any problems and started their extensive solar system trip. Many planetary scientists still rely on the unusual photos taken by the spacecraft's wide-angle and narrow-angle cameras, making their findings the stuff of folklore. Before the Voyager twins embarked on their amazing multi-decade journey of the large planets, humanity had only a rudimentary awareness of the solar system's far-off worlds, including Jupiter's tumultuous atmosphere, Saturn's shifting rings, Uranus's tilted axis, and Neptune's great dark spot. Their profound findings opened our eyes to a universe never before seen. Voyagers 1 and 2 captured the outer solar system in all its beauty through hundreds of photos, revealing it for the first time decades ago. Early in their journey, the Voyagers stunned scientists with their first up-close pictures of Jupiter's and Saturn's moons, exposing the presence of active volcanoes and fractured ice fields on worlds that astronomers had assumed would be as crater-pocked and lifeless as our own moon. In particular, 546 days after launch in March 1979, Voyager 1 arrived at Jupiter. In July of the same year, Voyager 2, which had a different course, also arrived. The VidCon cameras on board both spacecraft were built to be reliable platforms for generating full-color pictures through the employment of red, green, and blue filters. Their rotational velocity is more than 15 times slower than the crawl of a clock hand, so they rarely spin at all as they move across space, reducing the possibility of fuzzy pictures. The Voyagers captured almost 33,000 images of Jupiter and its satellites in total. It seems like each picture revealed something new. Rings around Jupiter, one of Jupiter's 53 known moons, Europa, has an ice covering that was shattered and believed to be more than 60 miles thick. A gravity assist gave the spacecraft a send-off push of 35,700 miles per hour as they exited the Jupiter system. They couldn't have escaped the Sun's gravitational pull and entered interstellar space without it. The Voyagers split off at Saturn. After dodging billions of dust grains while navigating Saturn's rings, Voyager 1 passed Titan, an orange-shrouded moon, and continued northward out of the planet's orbit alone. Voyager 2 proceeded to Neptune and Uranus. Voyager 2 discovered 10 additional moons around Uranus in 1986, adding the planet to the expanding list of planets with rings. However, the Space Shuttle Challenger's premature explosion after launch eclipsed Voyager 2's discoveries, which came just 4 days after the spacecraft's closest approach to Uranus. The 7 members of the Challenger crew perished, among them Krista McAuliffe, a New Hampshire high school teacher who was slated to be the first civilian astronaut. After 3 years, Voyager 2 observed the fastest wind speeds of any planet in the solar system, reaching up to 1,000 miles per hour while cruising at a distance of around 2,800 miles above Neptune's blue methane atmosphere. Triton, the biggest moon of Neptune, has a surface temperature of -391 degrees Fahrenheit -235 degrees Celsius, making it one of the solar system's coldest locations. 5 miles into the moon's atmosphere, nitrogen gas and powdered particles were ejected by ice volcanoes. If Carl Sagan hadn't been an astronomer on the Voyager 2 imaging crew, those pictures of Neptune and its moons would have been the last that either spacecraft took. After the official grand tour was over, NASA intended to switch off the cameras on both probes. The project had officially been renamed the Voyager Interstellar Project, although it had been prolonged in the hopes that the Voyagers would reach interstellar space. After Neptune, there would be nothing but unending emptiness and seemingly far-off stars for picture opportunities. NASA authorities were persuaded by Sagan to have Voyager 1 send out one more batch of photos. Thus, the probe pointed its cameras back toward the inner solar system on Valentine's Day of 1990 and captured 60 last images. Sagan's pale blue dot, the most eerie of them all, saw Earth from a distance of 3.8 billion miles. It continues to be the farthest depiction of our planet ever captured. Earth is hardly visible in the picture, its brightness veiled by sunlight reflecting off the lens of the camera. It doesn't even take up a whole pixel. According to Spilker, Sagan put a lot of effort into persuading NASA that it was worthwhile to take a closer look at the pale blue dot and realize how little it actually was. Sagan passed away in 1996. Voyager 1 entered interstellar space on August 25, 2012, marking the passage through the heliopause, the boundary separating the Sun's solar wind. As a testament to the persistence and dedication of scientists such as Carl Sagan, Voyager 2 followed suit in 2018. The two spacecraft are currently speeding across the solar system's vast outer regions. To put it another way, astronomers could never have imagined the Voyager's incredible adventures, which are far from done. Voyager 1 is now the farthest human-made object from Earth, having traveled over 15 billion miles at a speed of about 38,000 miles per hour. Like an uncle granted an exceptionally long life or an old automobile that keeps running, the robotic spaceship is an endless superachiever. It has attracted space enthusiasts worldwide. NASA's famous spacecraft continues to transmit signals to Earth from billions of miles away, providing fresh perspectives on some of the major enigmas of interstellar travel. These days, both Voyagers are so distant from Earth that it takes about 23 hours for a one-way radio transmission traveling at the speed of light to reach Voyager 1 and more than 19 hours to reach Voyager 2. They advance by an additional 3 to 4 light seconds each day. NASA's Deep Space Network, a triad of monitoring complexes positioned all around the world that allow continuous contact with spacecraft while Earth spins, is their only means of connection with Earth. The Voyager's transmissions are getting progressively weaker as they move away from us over time and space. Even nonetheless, the murmur has completely changed scientists' assumptions about what the Voyagers would discover when they began their interstellar trip. The scant observations from the Voyager mission have shown a complicated dynamic structure created by the interaction of the greater headwinds in the interstellar medium with the exhalations of our Sun. Both initially traveled across a zone known as the transitional heliopause border, where the interstellar medium and solar wind forces are delicately balancing each other out. The region beyond the heliopause is mostly unexplored, shaped by particle showers from the previous violent deaths of giant stars and galactic magnetic fields. The best way to describe our heliosphere is maybe as a wind sock that, as our solar system passes through the Milky Way, extends a long undulating tail behind it. On the other hand, it may resemble a straightforward bubble or anything in between these two scenarios, a croissant-shaped structure with two tapering trailing lobes. It's unknown right now, but one thing is for sure, most of the high-energy cosmic rays that bombard our region of the galaxy are blocked from reaching us by the heliosphere. These rays have the power to destroy the cellular machinery at the core of Earth's biosphere and change the climate on our planet. Therefore, in a manner, the solution to the riddle of how life began on a little planet orbiting an ordinary yellow star may lie somewhere almost unfathomably far away at the uncharted boundaries of our solar system. Following this, more data from Voyager over the next years might include vital information on the universe's beginnings for life. But what is the potential duration of the Voyagers? Perhaps we can have the missions extended until the 2030s if all goes according to plan. It's the limit, it all relies on the power. However, the Voyager's adventures will carry on even after they are utterly silenced. Voyager 1 will reach Proxima Centauri, our closest neighbor star, in 16,700 years, followed by Voyager 2 3,600 years later. After that, they will spend millions of years circling the galaxy. Long after the heliosphere has vanished and our sun has disintegrated, they will still remain in the universe, essentially undamaged. Not to mention, one dot of light blue, they might be able to deliver one last message throughout their journey. It won't be sent by radio, and if it is, it won't be heard by human beings. Two recordings, another type of antiquated technology, are used to convey the message. These aren't your typical plastic ones, of course, they're composed of copper that has been gold-coated and sealed inside an aluminum shell. Images and sounds intended to provide a feel of the environment from which the Voyagers originated are encoded in the grooves of the so-called golden records. In addition to the sounds of crickets, rain, and a mother kissing her child, there are images of kids, dolphins, dancers, and sunsets. 90 minutes of music feature Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good. Jimmy Carter, the U.S. president at the time the Voyagers were launched, also says, "We cast this message into the cosmos. We hope someday, having solved the problems we face, to join a community of galactic civilizations." This record represents our hope and our determination and our goodwill in a vast and awesome universe. The golden records are noteworthy for having an extremely extended shelf life. According to some astounding calculations, the chances of the golden record surviving extend beyond both the probable extinction of humanity and the collision of the Milky Way with the nearby Andromeda galaxy, past even the death of the majority of stars. This implies that one of the greatest cosmic riddles may eventually be revealed through the archives of the Voyagers. Throughout the many years that mankind has been studying the universe, we are the first to know with certainty that there are planets galore among the stars beyond our Sun. They are found in many different forms, and most of them are around the size of Earth. However, we have not yet found any proof of extraterrestrial life. Is life in the universe easily starting and widespread, or is it extremely uncommon? However, answering one question just raises others, as with most scientific inquiries. Which of these exoplanets, if any, are home to life? How long does life endure, and how fast does it begin? The Fermi paradox is the moniker given to the unsettling quiet of the cosmos. Where is everybody, is a famous question made by physicist Enrico Fermi. The billions of years that the cosmos has existed provide sophisticated technological life forms plenty of time to transit the galaxy, even at sluggish speeds. Why then is the universe so silent? In the meanwhile, some of the variables in the hotly contested Drake equation, a series of numbers that might eventually indicate the number of sentient civilizations we should anticipate to find, have been filled in by exoplanet discoveries during the past 20 years. The majority of its parameters, such as the percentage of planets having life, intelligent life, and observable technology, are still undefined. However, the equation itself implies that we could find a solution eventually. Compared to Fermi's paradox's quiet pessimism, it seems at least a little more optimistic. The Drake equation was a significant scientific breakthrough when it was initially proposed, offering many fascinating insights. For instance, one seemingly unanswerable question, how many intelligent, spacefaring civilizations exist in our galaxy today, was, for the first time, divided into a manageable number of components that we could imagine addressing one at a time. These components include the rate of star formation in the Milky Way, the proportion of stars with planets, the average number of potentially life-supporting planets around stars with planets, the percentage of such planets that develop life, the percentage that develop intelligent life, the proportion of intelligent civilizations that emit detectable signals, and the duration of time such civilizations continue emitting those signals. By multiplying these factors, we can estimate the number of active civilizations we may identify today. However, we immediately face significant challenges. First, while we know rather well the rate at which stars develop in the Milky Way because we've measured it, increasing the star formation rate to the universe's age would yield essentially no stars. Since the hot Big Bang, we estimate that the Milky Way has formed approximately 10 billion stars, a figure that, while large, represents just 2 to 3% of the estimated 400 billion stars in our galaxy. The reason this approach to determining the total number of stars fails is simple: the rate of star creation has fluctuated over cosmic history. Stars did not form during the first 200 million years of the universe's existence. Star production peaked after rising during the universe's first 3 billion years, then declined thereafter. Locally, bursts of star formation likely occurred when we absorbed smaller satellite galaxies, and another burst may be beginning as the Magellanic Clouds and Andromeda gravitationally interact with our galaxy. Yet, these variations in star formation rates represent only the surface explanation for the Drake equation's challenges. The fundamental issue lies in the assumptions underlying the Drake equation when it was proposed. At the time, the cosmos was believed to be timeless and unchanging. We now know this assumption is incorrect. The universe has evolved from a hot, dense, energetic, and rapidly expanding state, a hot Big Bang that occurred a finite duration in the past. A more fruitful approach involves computing quantities we can reasonably measure and proceeding responsibly toward the cosmic unknowns. Unlike 60 years ago, when the Drake equation was first proposed, we now have a superb understanding of the universe, including the Milky Way and the local group. We know about different star populations, the processes that lead to heavy element formation, rocky planets, and complex chemistry, including energy-storing molecule synthesis. Additionally, significant progress has been made in exoplanet research. Just 30 years ago, we discovered the first planets around stars other than our Sun. As of July 2024, there are approximately 5,700 verified exoplanets. While biases exist in our data, favoring easily detectable planets, we have mechanisms to account for these biases. Our knowledge base about the Milky Way today allows us to use concrete data instead of speculation. We know the number of stars, their population distribution, the number of planets per star, the proportion of planets with elements supporting complex chemistry, and the number potentially habitable for life. From this perspective, estimating the number of possibly habitable planets in our galaxy becomes straightforward. To demonstrate, 80% of the Milky Way's 400 billion stars are red dwarfs, 18% are sun-like, and 1 to 2% are too large and short-lived for life to emerge. Each solar system likely has 5 to 10 planets, with 1 to 2 potentially in the habitable zone. About 20% of planets around sun-like stars are Earth-sized, with a higher proportion among red dwarf stars. Assuming red dwarf systems are uninhabitable while sun-like systems are, we can calculate 400 billion stars times 0.20, Earth-sized planets, times 1.5, potentially habitable planets per star, times 0.18, sun-like stars supporting life. This gives us approximately 21.6 billion habitable planets in the Milky Way. Such precision is unnecessary, 20 billion suffices. However, ambiguities exist. The number of stars could be as low as 200 billion. Some stars may lack enough metals, heavy elements, to support planets with life, though this proportion is small. Likewise, certain stars may lack planets, though this percentage is less than 20%. Adding another 33% uncertainty to our estimate reflects these variables.